next one. Oh, and we're done. Next time, center of mass. Ooh, boy. Next time is center of mass. This one's rough. I think I want to go. Okay, so today we're looking at center of mass. What is the center of mass? What role does the center of mass play? And how does that build into this idea of conservation of momentum? All right, so why do we calculate and how do we calculate? Maybe we'll start with the how. How do we calculate the center of mass? Well, the first thing you need to know is that the center of mass is also the center of gravity, another way of saying it. Okay, so it's the center of gravity, which means that it is the average position of a collection of particles. That's how we're going to treat it. Now, these are weighted. So this is a weighted average, weighted according, because think about it, something heavier is going to have more oomph, so to speak, according to their relative masses. Okay? What else do we need to know? Center of mass, since it's center of gravity, it is also the balance point. Of an object. Okay? Now, if it is symmetrical, then it is at the center of mass, COM, is at the geometric center. Now, there are two ways we can calculate the center of mass. The easy way, which is the algebraic way, which means that the x-coordinate of the center of mass is going to be the sum of all the masses times their location, divided by the sum of the masses. The y center of mass is going to be the same thing, only except for y's. The sum of the masses times their y coordinates divided by the sum of the masses. Now, calculus takes this a little differently. The x center of mass is now going to become, instead of a summation, in summation and algebra would flow into an integration in calculus. So it is going to be the integral of all of the x's locations, basically, times an infinitesimally small amount of mass divided by the integration of all of those masses. The y center of mass is going to be the same way. Notice that the sum of the masses becomes the m is the slice. We're taking little bitty slices, and I'll explain this to you when I see you in class. We're taking little bitty slices, almost like little pages off of a notepad. Each one of those represents an infinitesimally small amount of mass, and we're going to add them all up and get the total mass, okay? Each one of those is at a location, and we can figure that out. So now it's going to be the sum of the y coordinates times the little slice of mass divided by the integral of the masses, okay? So, the velocity of center of mass, just so you know, is the derivative. Think about it. Velocity is derivative of position. So it is the velocity of the derivative of the center of mass with respect to time. Okay? It says derive an expression for a center of mass for the shape shown below. Both rectangles have equal masses. Okay, so this is one of those where, since they are geometric shapes, they're fairly easy geometric shapes, and we can look at each one of them separately. We can do this algebraically. It's not an odd shape. If it's not an odd shape, you can use algebra. So let's find the center of mass. Well, where's the center of mass of the bottom piece going to be? If this thing is uniform, it's uniform density, etc., then the center of mass is going to be right in the middle, isn't it? Okay, well, where is that? Well, if this goes from 0 to L, this point right here is going to be at L over 2. And then if this is from 0 to W this way, this is going to be at the y coordinate W over 2. So easy enough to figure out. Now we got to find the center of mass at the other one, which will be here, won't it? Let's change colors. That would be here. So how do we figure out what that is? Well, this is width W, isn't it? Okay, so this is width W. Well, it gets a little bit more complicated here, doesn't it? So now we got to figure out what this is. This is L, and I'm going to show you. To go all the way to this point right here, we just have to take all of L, and subtract out this little chunk right here. So what is this little chunk right here? This little chunk right here is going to be W over 2, isn't it? So the x coordinate is going to be L minus W over 2. And now let's see if we can figure out what the y coordinate is. So if we look at the y coordinate, we can look at it the exact same way. We have what? We have all of W. Right here we have all of W. And then we've got half of that. That'd be pretty easy to figure out. What is half of that? Well, this chunk right here, sorry, put this in a color. This chunk right here would be in half of L over 2. So half of that would be L over 4. So this is going to be W, this chunk, plus this. So W plus L over 4. Okay. So now I have two centers, and now all I have to do is find the center between those two centers. So where's the center of mass between those two guys? Okay, so let's figure that out. The x center of mass, we're going to use our formula, which is the sum of what? Sum of mx over the sum of the m's. Okay, so let's figure out what they are. Both rectangles have equal mass, so they're equal masses, so this is going to be 2m at the bottom. We'll call it big M and big M. So this is a mass big M and this is a mass big M. So we know already it's over 2m. Well, this is going to be big M times what? L over 2. That's this guy. Plus big M over the location of the other guy, which is this one right here. L minus W over 2. Okay, well, what is that equal to? ML over 2 plus ML minus MW over 2. Okay. So what do we get? We get 3/2 ML minus 1/2 MW, and this is all going to be over 2M. Well, I want you to notice something. What happens to the M's? The M and the M and the M and the M go away. And then we just multiply. Well, shouldn't have probably done it there. This is still M. I skipped over, but the M's go away. And now what happens? We get what? We get 3/2 L minus 1/2 W over 2. Over 2 is the same as multiplying by 1/2. So we end up with 3/4 L minus 1/4 W. Okay. So we go 3/4 of the way, which would be, here's halfway, here's a fourth, here's another fourth. So it's going to be somewhere right around here. And minus 1/4 of W, so that's going to bring it back just a little bit. So it's going to be somewhere along this line right here, probably. That makes sense, doesn't it? That's about halfway between those two dots in the x direction. I bet I can figure out what the other one's going to be too. About halfway between here, and the y direction is going to be right about here. So I'm betting it's right I'm willing to bet that it's right here is going to be the center of mass of that system. So let's look and see. Let's look for the y center mass. Y center mass, we're going to do the same thing. We're going to do the sum of the masses in the y direction divided by the sum of the masses. So we have big M times W over 2. That's for the first guy right here. And then we have big M times W plus L over 4, all over 2N. So if we're smart, we'll go ahead and get rid of our M's. And so we end up with W over 2 plus W plus L over 4. I'm going to multiply that by 1/2. We got 3/4 what? We got 3/2 W, so we have 3/4 W plus L over 8. Okay. And that does look like we have about yeah. Okay, so that puts us 3/4 W would be right about here, but then we have L over 8, which is another chunk like that, which would put us right up about here. Okay, so we're right. We are right on. So our Y center of mass for the total system. So if we do X center of mass, Y center of mass, X center of mass, Y center of mass, because it's a coordinate pair, is going to be what? 3/4 L minus 1/4 W, 3/4 W plus L over 8. Okay, and that's how you find center of mass algebraically. Don't get lost in the weeds of, you can sometimes just kind of figure where it's at. You can kind of figure out where it's at and estimate, especially in multiple choice, to get answers. We'll practice that some in class. All right, so let's look at the next one. The next example, we've got this dude, pretty cool, T-Pain, who has a mass of 80 kilograms, is on a 240 kilogram boat. He walks 2 meters per second relative to the boat, starting from the back of the boat, walking towards the front of the boat. The boat is 1 meter long. What's the velocity of the boat relative to the water? Okay, so we want to know the velocity, center of mass, okay? We know that is equal to the sum of the mass times the velocity over the sum of the masses. That would give us the velocity, wouldn't it? All right, so what you got to realize is the center of mass of a boat person system can't move relative to the water as there's no outside force. Walking across the boat is an internal force to the system. As he walks across the boat, you know he's going to move forward as much as the boat's going to move backwards, but it's all going to equal out. So it's can be kind of confusing. He'll move forward to the front of the boat will move backwards, but they'll only move half that distance, believe it or not. It's kind of strange the way it works. If T-Pain walks one direction across the boat must move in the opposite direction. So the center of mass, the reason they do that, equal and opposite, is so the center of mass does not move. So the center of mass was 0, so it's going to stay 0. Get it? So we know the center of mass is going to be 0, which is pretty cool. So the velocity of the center mass is 0 also. So the center of mass will not move in this type of system. It's constantly readjusting. Okay? So as his mass goes forward, part of the boat's going to have to go backwards to compensate. It's pretty interesting how it works. Okay, so we know that 0, which is the velocity of center mass. So what is the velocity of center mass? The sum of the mass would be the mass of T-Pain times the velocity of T-Pain plus the mass of the boat times the velocity of the boat divided by the mass of T-Pain times the mass of the boat, sum of those, okay? So now let's see if we can solve for the velocity of the boat. Let's see what we get. Oh, this should be interesting. So what are we going to do here? How do we solve this? First thing we can do is what? All right, so we can cross multiply, that goes away, so we're left with the mass of T-Pain, velocity of T-Pain equals the mass of the boat, velocity of the boat. Okay, that makes sense except negative. We're going to cross multiply this and it's 0, and then we're going to bring this over, okay? So let's fill in. Mass of T-Pain is 80, he's moving at 2. Mass of the boat is 240, and we want to know what the velocity of the boat is. Okay, so we just divide both sides by 240, divide by 240, we get negative 160 over 240, which is equal to negative 0.67 meters per second. Okay, all right. It's going to move slowly. He'll move more quickly. He'll move more slowly. The boat will move more slowly. Why? Think about it. The boat weighs more. He's going to move faster. Boat will move more slowly. He weighs more. So now, if T-Pain walks 8 meters across the deck of the boat and starts on the very left end of the boat, how far does the boat move? So how do we figure this out? Well, the X center of mass is going to be equal to what? Mass of T-Pain, position of T-Pain, plus the mass of the boat times the position of the boat divided by the mass of T-Pain and the mass of the boat. So let's see, mass of T-Pain was what? 80 times his position is at 0. If we call this our 0 position, that goes away. Mass of the boat is 240. Its center is going to be halfway. So if the boat is 1 meter long, it's at half a meter, so 0.5 divided by 80 plus 240. So it's going to end up 3.75. Let's double check that. 240, 120 divided by, I'm sorry, that is incorrect. If the boat is 1 meter long, oh no, 8 meters across the deck of the boat. What am I thinking? I'm sorry, this boat is 10. Hang on. Your teacher needs to check something up here. Let's look. How long is this boat? And it says 1 meter. It's supposed to be 10 meters long. How can he walk 8 meters across the boat? This is 10 meters long. That makes more sense. X is 5, the center. So this is 5. So this ends up as 3.75, which is what I thought, meters long. Okay, that's where it starts. Now let's look at it afterwards. We know the center mass is still here. He's at 8. So how far is the center of mass now? Where is the center of mass at this point? Still the mass of T-pane, location of T-pane, mass of the boat, location of the boat, divided by that 320, because that didn't change. 80 plus 240 did not change. So T-pane's mass is still 80, but now his location is at 8. The mass of the boat is 240. Its center is still at 5. Divided by 320, what do we get? We get 5.75 meters. And this is from the left end of the boat. So how much did the boat move? Well, if it started, the center mass of the whole system moved the difference between those two. So 5.75 meters minus 3.75 leaves me 2 meters. So it moves 2 meters. Which direction though? The center of the mass shifted. It started at 3.75. So from here, the center of mass started right about here, 3.75. Now it's somewhere over here at 5.75, right? Okay. So now what happened? It shifted to the right. I mean, the center of mass of the boat shifted to the right. It says, how far does the boat move? So if the center of mass shifted to the right, the boat must have moved in the opposite direction to compensate for that. If he's going this way to the right, then the boat must have moved to the left. In other words, opposite. The center of mass of the boat moved opposite the direction he was moving. Okay? So now what? Oh, here comes calculus. This one's going to be exciting, folks. Here's where we go. So far, you probably should feel pretty good about this. Okay? So how do we do this? It says find the center of mass of a rod, length L and mass M. Well, this thing is symmetrical about the Y and Z if you want to think about it. So we know the center of mass is going to, first thing we know is it's going to fall somewhere right down the center here, isn't it? So I don't really need to worry about up and down. It'll be in the center somewhere. We just don't know where. So we know in the y direction, the center of mass is going to be at the center because it's a perfect circle, and that's cool. Okay, now we have a linear density. Since we're only going to find this in the x direction, okay, so here's how we figure it out. We're going to take a slice. We don't know what that slice is. We got to take a little bitty slice. That's what this is. This is a little chunk of it we're taking, and we call that dm. This is what I call micro, okay? We know, let's start with what I call macro, which is the whole thing. We know we are taking a linear mass density. Since we're only going in the x direction, this is linear mass density because it's just in a straight line. And we know the linear mass density is lambda divided by, it's m over L, okay? That's density. Density is mass divided by volume usually, but this is just linear, so it's mass divided by the length, okay? So that's our macro. All right, so now here we go. So instead of this guy, let's rearrange our macro. We have density equals mass over length, but I want the little slice of mass, so I'm going to length, not 4. So I'm going to rearrange this to have big M equal lambda L, and we're going to do this. Lambda is a constant, so when we go from macro to micro, M becomes dm. This is a constant, and length becomes dl because we don't know the location. We do know, however, we want to go all the way down the length of it, so we're going from 0 all the way down the length of it, which is to L. That's our limits of integration right there. So we're going to start and say that the x center of mass is equal to the integral of x dm over the total mass, which is m. If you sum this whole thing up, if the mass is m, it's m. You don't have to do an integral there. Now we're going to start plugging in. So we're going to do 1 over m times the integral. We're going from 0 to L, our limits of integration. We've got x. We want to plug in for dm. dm is what? Lambda dl. Well, what is L? It's an x location on the x-axis, so this becomes lambda dx. So lambda dx, which is cool because now we're integrating with respect to x, which is the coordinates that we know. So now let's actually do this. We can bring lambda out here. We can bring m out here. Integral location from 0 to L. And we've got x dx. Lambda, however, we have a definition of because that was our macro to start with, wasn't it? Lambda is m over L. So now we're going to do m over L over m. M is going to go away. Integral of from 0 to L of x. Let it come back. X dx. All right, so this is the opposite of taking, so we've got 1 over L here, because remember this was divided by, so we've got 1 over L, and the opposite of taking the derivative. In other words, what derivative would you had to have taken? Just like the opposite, we would say x is going to go up to x squared, and then we would have to divide by that same number to get rid of it. So if we, in other words, if we took the derivative, guys, this is what I'm talking about. If we took the derivative of this right here, with the x, wouldn't it? And we're going to do this all the way from 0 to L, okay? So we have 1 over L. I don't know why I keep doing 4. This is the second time I've done that today. 1 over L. All right, so 1 over L, and we're going to plug in from L to 0. So that would be 1/2 L squared minus 1/2 0 squared, which of course is going to go away. So we're going to end up with 1 over 2L times L squared. Got an L that goes away, so we're going to end up with 1/2 L, which, if you think about it, is not surprising. If you have a rod that's uniform, then where should the center of mass be? The center of mass should be in the very middle, shouldn't it? Okay, so that's how you do that. All right, now we are going to practice this a lot more in class next time. This is just your first intro to it. Just the big thing to remember is, on this one, is if you're in the x direction, it's this guy. And you need to remember this idea of macro, micro. And we'll do a little bit more next time. Until then, bye-bye.